All right, so in this video, we're going to be starting to look at some time series analysis. And so we're going to pull in some data sets that we can explore. So the first one is New Hampshire temperatures. And if we were to look at this data set, we can look at what kind of time series it is. We're also going to pull in a data set on seatbelts. And we're going to look at some sunspot data. And these are all built into R. Now, if we want to look at the data, we have a couple of different choices. We can just print the data to the console. So it gives us information about the year that it starts, the year that it ends, the frequency, and then all of the different values. You can also do the view function that we've used for looking at other data sets. So seatbelts. If we run that, then we can view it just like we would any other data set. In this case, there was a change in the law at some point, presumably that mandated seatbelts. And so these are fatalities and injuries from crashes. And then, of course, the sunspots. Now, the way that the sunspot data prints, there's a lot of data here, but this one is separated into months as well as years. And so it plots in this grid, not just as a list. So we can see that we have observations going back to 1749, starting in January, and then we have monthly data for all of these years. And it actually stopped after a certain point because it's too much to print. So again, there are different ways that we can look at this data. Now, if we want to extract an individual time series from a data set like seatbelts, we can do that. So the number of drivers killed in our seatbelts data set is in column 1. And so I'm just going to pull that out as a separate vector. And now I can just look at that separately. And again, this one has information based on year and month. I can also plot my data sets, my time series. Now, when you, by default, attempt to plot a time series, it is going to plot as a line graph. And you can see we have different kinds of behaviors on our different time series. This has a lot of data, and so you can see it's quite dense. Now, if you plot a data set that has lots of different time series in it, then they will plot as these separate plots. We can zoom in and get a little bit better look at the different variables that are plotted, but they're all plotted on separate graphs. We have quite a distinct behavior in the petrol price. It looks interesting. And we have, again, a very distinct one in the law because they were all 0 and then the law changed and it immediately became 1. It's not a random type of thing that's varying. So we do see some seasonal behavior in some of this data where it's very high and then it's very low again. So that might be something that we can explore later. Now, you can also add other kinds of components to our plots that we've seen in other examples from earlier on in the base R plotting. So we can add things like a title. This is New Haven temperatures, not New Hampshire. Type B and Y lab equal temperature. And so again, it's plotting the dots, it's connecting them with little line segments. We've added a title. And so you can add extra features to the graph to specify what kind of variables are being plotted. If you zoom in, the temperature graph is actually, the label is actually quite off the screen there, which is interesting. Now, there are several packages that are designed to deal with time series in particular and actually do a better job than base R with the plotting. And so one of those packages is TSstudio. Again, if you've never run it before, make sure you install it from the tools menu. And then we can do a time series plot from the TSstudio package to look at these graphs. And again, this is a little bit more interactive. You can see where the various points are on the graph. It's color, it has a little bit of color. And so we get a little bit more, we can actually zoom in on the data and then zoom back out again. You can scroll through the data. So again, the TSstudio is designed to be a little bit more interactive and shows up on the viewer rather than the plot screen, but a little bit more interactive than some of our other static base R plots. We can look at our killed data. And this is quite nice for the sunspot data because the sunspot data is quite dense. And again, we can sort of zoom in, we can choose a window to zoom in on, and we can see sort of much more detail. So let's say we wanted to look at 2 sunspot cycles. We can zoom in on those, and you can see that sometimes the sunspots go all the way down to 0, and you can sometimes get quite a lot. Now, we can also, of course, with the TS plot, we can also add some additional features to our graph. We can add a title. So monthly sunspot observations, X title, that is a capital X, and Y title is number of sunspots. And then we can also add a slider to make it easier to sort of zoom in on our graph and look at additional details. So again, here's our slider. So for instance, if we just want to look at the last couple of decades, sunspot cycles are 11 years long. And so you can see from about 1965 to the next minimum is around 1976. So about 11-year cycle. And you can move both ends, by the way. You can also, of course, change the color. So if I wanted to, for instance, or the thickness of the line. So for instance, I could add in color equals black and width equals 3. Again, I can get a slightly different appearance to my graph. I can also make other kinds of style adjustments. So for instance, I can use a dashed line or other kinds of features. So let's start with our, let's say, New Hampshire temperatures. I can add a title, temperatures in New Haven. X title is time. Y title is temperature. And I can also do a dash. And line mode equals lines plus markers. And again, you check the documentation for what all of the various options are. Now, if we look at what happens when we do a data set that has multiple plots in it, like we saw with the seatbelts plot, in base R, we get a bunch of little different subplots. In TS plot, in the TSstudio plot, it's going to put all of them on the same graph. So you can kind of see the difference in the sizes as well. So this is KMS, kilometers per second. So that's a lot larger than, or KMS is much larger variable than some of these other variables. You can also separate them out into multiple plots. And so you can, what you're looking for here more or less is things like general behavior, seasonality. If you hit zoom, then it will pop up into a window and you can look at the window with a little bit more detail. When you have a lot of variables like this, they are quite compact and they're not like in columns like they were in the base R graph. So I think the height here is a little bit difficult to see exactly what's going on. It's hard to see some of the features. Even when you fill the screen, it's difficult to see all of the features. But this can be very useful if you have just a couple of time series graphs in your data set. Now, we can also extract information from our data sets. For instance, when does the data set start? So the sunspots data set has a starting time of January 1749. When does it end? This particular data set ends in 1983 in December. We can figure out how the time is incremented by looking at delta t. And this is a fraction for 1/12, so 1/12 of a year, so monthly. We can look at the frequency. So 12 times per year, that's another way of sort of looking at the delta t. We can look at the total time. So these are all the time values. for our data set. So this might be useful, for instance, if you're trying to extract the time values in order to convert this to a data frame for other kinds of analysis. So this is a way of getting all of the time values. We can also look to see if there is a cycle. And then also we can check to see, is it a time series? And it will come back as either true or false. Now, some aspects of time series analysis require that our data be stationary, which is to say that it has no trend and it's basically just random noise. So we're going to create an example of this. So this is essentially using an ARIMA model to simulate stationary data. And we're just going to get 100 values of it. We'll say more about what ARIMA models are like in future videos. And then we're going to plot it. Just to see what it looks like. And again, you can kind of see there's no pattern. It's up, it's down, it's kind of all over the place. This is kind of what you would expect from random noisy data, where again, there's no trend. The things just kind of hover around zero, a little bit up, a little bit down. You can also sometimes encounter data sets where there is a sort of a random walk trend, where errors are essentially correlated with each other. And again, we're going to use a similar ARIMA model to simulate this, although in this case, we're going to use a model of order 0, 1, 0. The one in the middle is the integrated part of the ARIMA auto regression integrated moving average. And that integrated component is the random walk component. And what does a random walk look like? It's going to kind of look like this. So it's kind of meandering in a particular direction for a while, and then it changes direction, and then it meanders in that direction for a while, and then it again. So it's not quite as sort of up and down all over the place as we saw with the stationary model, but this one has a little bit more structure to it, but it's still wandering in a particular direction, but then changes direction. Now, sometimes we want to find out how many times we need to subtract values in the model in order to get it to be stationary. This tells us information about the trend and allows us to account for some of the different components of our ARIMA model that we're going to eventually want to construct on this data. And so what we can do is we can calculate the differences between values using the diff function. This is a common time series analysis approach. And then if we plot the differences, again, what we're looking for when we plot these differences is we want to be stationary. So we want to see if one set of differences that would suggest maybe there's a linear trend or a random walk trend that we can subtract out of our data. If I do the same thing on the killed, the number of people that were killed in car wrecks, again, noisy. This is what we want for it to be stationary. So it didn't look like this when we were just looking at the original data, but now when we take one set of differences, we do get something that looks more random and therefore stationary. Now we can also do this for the sunspot data. Now, if there is seasonality or we need more sets of differences in order to get to stationary, then we can calculate the differences and then keep calculating them until we get something stationary. Again, this looks pretty random at this point. Certainly, we see some cycling going on with these collections of things, but there's a lot of data here, and this is still, again, looking more random than it was looking before, where we saw these clear cycles. Now, we could also try dealing with the cyclical data by putting in information about the how far apart the cycles are. So we could calculate something like the differences in the sunspot data and then put in a lag value that is equivalent to the cycle length. So if the months are counted as 1, then we could put in a lag of 11 times 12 because sunspot cycle is 11 years. That would be 132 lags. But since the individual observations are counted as 1/12 of the year, then our lag would be 11 because that would be 11-year cycle. So it's important to know how the data is being encoded in order to determine what the lags stand for. And so essentially what we're doing here is we're comparing one part of the cycle to the same part of the cycle. Now, you can do things like correlations on time series data. It is basically numerical data. So we can calculate correlation plots on the different variables, just as we did before. This is all the correlations of all of the different components. You can, of course, construct plots of those variables as well. You can look at pair plots of the data. We looked at a pair plot function from the package ggally in a previous video. There's also one in base R. Again, lots of variables here, so it's really hard to see these. You can zoom in a little bit to see the correlations or the relationships if they exist a little bit better. But this is a way of looking at the data. And we can also create histograms of individual variables. This is actually another way of assessing some of our model assumptions as we go later on to model things. If our stationary data is really stationary, then what did we call that? We called it white noise. That was what we called it. If our data is truly stationary, then we should get something that looks approximately randomly distributed. That was simulated random noise. We could also, for instance, look at some of our differences calculations, say diff1. And again, depending on the number of observations, what we would hope for is we would get something that looked at least approximately normal if it's truly stationary. And of course, another way to assess normality is with a QQ plot, a normal probability plot. And we can assess the normality that way. And again, we have histograms, we can do box plots to look at the shape of the distribution. We can do normal probability plots to do other kinds of assessments of normality. So all of these plotting functions are available to us for time series data. It's just going to plot the outcomes, not the time itself, but we want to see how those outcomes fare relative to, again, model assumptions that we're going to make as we begin to model the data in future videos.